Presentation. Does anyone in public have any question? No. Okay, thank you. The next lecturer for today is Nick Duinslaeger from Spain. Dear colleague, you can start with your presentation.
Do I just okay, cool. So good morning, everybody, and yeah, thanks for the invitation. Happy to be here. In our group in Spain, we are basically working with persistent contaminants, and like in the scope of water reuse and circular economy, it's quite important since we're reusing, making a cycle of water, and to make sure that these don't accumulate and that we have a solution for this. And one topic I really wanted to focus on today was one that is basically very topical these days, and one I'm working closely on myself, and that is the topic of PFAS. Okay. So basically, with this presentation, I wanted to, since basically we've been seeing this this topic in the a lot these days. No problem. A lot these days in the media, I really wanted to take some time to kind of understand basically what are PFAS, because it's been talked around. This term has been thrown around a lot. But I think it's important to understand what they are, what the issue is, and what the gravity of the issue is, and what the peculiarities are of these PFAS. So basically PFAS, which is short for perfluorinated substances, is just a general name. It's a generic family of different chemicals. And with the new definition of the EPA, well, they kind of hold more than 9,000 different substances. And that's already the first thing that makes it quite difficult to kind of focus on these PFAS or talk about them, because basically it's a very big group and they all behave differently. So, well, yeah, that's the first thing. So they're man-made, so they do not usually occur naturally in the environment. And I think we've been all, well, we have them a lot closer in our lives than we actually think. I think maybe a lot of you already seen the movie Oppenheimer, which came out lately. Well, these PFAS have been used or produced since the 1940s, and basically they came out of like an accident in the lab where they were discovered, and then were quite critical in the Manhattan Project. So I would say like they're influencing our lives now, but they have been for quite some time. So they've been used since the 1940s, as I said, in many different industries. And that's because these PFAS are actually they have very useful properties. So they can make products that are very resistant to heat, to oil, to grease, stain, and water resistance. And that's why they are used in many different consumer products, as we will see later. Like I said, it's a group of more than 9,000 substances, and that's because they have many variations. So you can find them in a branched, unbranched. They have a long, short chain, and I will explain shortly what that actually means. So if we talk about PFAS, the most prevalent ones, or the ones that you will hear most these days, are PFOA and PFOS, but there are many others. And maybe let's quickly take a first chemistry lesson. So basically, this is a representation of PFOA. And you can see it's basically made out of a carbon backbone or a carbon chain, which instead of having hydrogen on these carbons, basically they've been interchanged with fluor. And you should know that fluorocarbon bond is one of the strongest ones, covalent bonds in organic chemistry. So you can already imagine, since we put all of fluors, this chain length full of fluor, that kind of stabilizes the molecule and makes it a very strong and persistent molecule. As I said before, so here you can already see this chain can be short chain PFAS, or long chain PFAS, and it can also get branched. You can put oxygen between them, you make an ethers, etc. So you can kind of really play around with the chemistry of these molecules. What is peculiar is that they have two kind of different let's say, parts, which is the chain itself, which is fully fluorinated or almost fully fluorinated in some cases. And then you have the head group, which is basically this carboxylic head group and they interact completely different. So basically the interaction of the head group that can interact with polar molecules, but then on the other hand, the fluorinated chain that acts more in an apolar way and in a hydrophobic way. So you have both lipophobic and hydrophobic properties in one molecule. Like I said, we can go a little bit in the classification into PFAS of PFAS, but it's very wide. So I'm just gonna explain these. Well, the two major ones or more prominent ones that are talked about, and these are PFOA and PFOS. So PFOA is basically a carboxylate or a carboxylic acid because the head group is a carboxylic acid. And then in case of the PFOS, it's basically a sulfonic acid because it has a sulfonic head group. As I said before, these PFAS are a lot closer to our lives than you can actually imagine or that you may think, because they're so heat resistant and, for example, water resistant, oil resistant. Well, they've been used in many different consumer products, like, for example, non-stick cookware. I think everybody knows Tefal pan. But also in pesticides, in paints, in shampoos and cosmetics, fast food packaging, of course, because it's grease resistant, in photography. And a very specific one, a particular one, is firefighting foams, which I will come back to later. And what happens now? So basically, the industry has been using them, having very advantage properties. So it ends up in all these consumer products. These consumer products or end up in waste bills or belts, or they basically end up in the environment itself. And basically, these PFAS are leaching out of these products, entering the environment because well, since they're so resistant, the conventional and even more advanced wastewater treatment processes or technology are inefficient in removing them or degrading them. Maybe shortly, because these firefighting foams are also very, this term also gets thrown around a lot. So basically, what are they? The AFF stands for aqueous firefighting foams. And these foams basically consist of PFAS because they can form sort of a covering layer of film to cut off any hydrocarbon fuel fire and basically extinguishing the fire. These are used usually a lot of in well, the aerospace and in different army and military bases. So what's the problem now with these PFAS? As I said, these molecules are very extremely persistent, and that's why they got the name forever chemicals. Probably you will also see them in the media with this name. And that alone wouldn't be a problem, but since 10 years, studies have shown basically that they're very toxic and even have been linked to different types of cancer. So the most prominent ones are thyroid disease, liver damage, even kidney cancer, but there are many more different basically negative health impacts that it can have. So you can already see the problem occurring. They're very persistent, so we cannot get rid of them. They're very toxic to us. And moreover, depending also on the type of PFAS, they're very mobile in the environment. So since they're very mobile in water, they will basically pass on in the environment quite quickly and quite easily. Getting taken up by plants, for example, animals eat these plants, other animals eat these other animals, we eat animals. Well, they start to kind of bioaccumulate in the food chain. As I said, the conventional treatment and even more advanced treatment technologies have not been able to deal with these PFAS. And an addition to the problem is that since PFOA and PFOS are being regulated, so these most well-known and used in history, well, industry just said, okay, let's just switch to other types of PFAS which are not regulated, and we'll solve the problem like this. Well, it's getting worse because basically how they switch to shorter chain PFAS since they have the exact same objective. But these have shown to be more persistent, even more mobile in the environment, soluble, and also more dangerous to human health. So to give you a little bit of an idea of the gravity of the situation, well, some studies have come out and shown that in many parts of the world, these PFAS levels in rainwater already are exceeding established safety limits. So you can see here, many studies have been done in China, but also in Europe and the USA. And if we look at PFOS and PFOA, in many of these cases, they're already exceeding safety limits, and that is in rainwater. So you would say like it's already quite diluted to quite difficult to get persistent contaminants in these. Well, their already concentrations are quite high. Next one to kind of like focus on the gravity of the situation. I want you to bear with me because we're going to do a small, we're going to calculate a little bit the societal cost of PFAS. So there are basically 12 main PFAS chemical producers in the world. So we probably know a few of them, 3M, DuPont, BASF, Bayer, etc. So the list goes on. But what is important to know is that the global market size of these PFAS is around 28 billion euros per year, which is equivalent of 3,280 billion of dinars, to get a bit of an idea. So that is in the production, in sales, etc. But you can see like after well, these 12 main companies are having we're getting a profit of nearly 4 billion euros per year, which is quite a lot. So you can see it's quite a big industry. But then if we check what society is actually paying, everything related to health, health and remediation, well, that is estimated around 16 trillion euros per year. So you can already see there's a disbalance, and if we now average it out with the amount of PFAS produced and sold in a year, well, the average price or the let's say the profit that these companies are making per kilo is around 19 euros. Not bad, but the average societal cost of PFAS per kilo is about 19,000. So we're paying 1,000 times more to remediate, to help people with health effects from these PFAS, just to deal with them. So I would say phase out is kind of like where we should go or head to. Like I said before, these conventional treatment technology, I think Julien also talked about it before, not very efficient in dealing with PFAS. Luckily, there are some technologies that are trying to deal with them, and the most mature ones I will talk about now. We can divide them in two different terms. So we have removal technology, which basically, as it says, kind of removes the PFAS from the waste stream. But then basically you're just dislocalizing the problem to another matrix. And then the other big group would be the destruction technologies. So within the removal technologies, there's a few of these that you probably already know. So granular activated carbon, which looks a little like this. So granular activated carbon in filters, we pass the water through it. They supposedly would need to absorb PFAS from the water, and then you get clean water in after the filter. The problem here is, as I said, all of these different PFAS, they kind of behave in a different way. So especially if we look at shorter chain PFAS, they don't really get retained by the activated carbon. So not an ideal solution. The same with ion exchangers. So basically, it's the same concept, just you exchange the granular activated carbon with a sort of an ion exchange resin that will interchange another ion for PFAS ions in the water. But there we see the same issue arising. So these short chain PFAS and other types of PFAS are not really as well retained as long chain PFAS like PFOS or PFOA. And then we can also do nanofiltration. That seems to be working better, but still is not a 100% safe, or let's say efficient. One of the upcoming removal technologies, I would say, is foam fractionation. And if you remember, we talked about the PFAS tail or the chain, which is fully fluorinated. Well, this will act very hydrophobically. And then you have the head, which is hydrophilic. So what happens now with if you bubble just air through a solution of PFAS, well, these PFAS will partition in such a way that they will cover basically the surface of these bubbles. And with this it's kind of an interesting technology because it doesn't use a lot of energy. In this way, they're able to basically filter out or take out these PFAS, since they will adhere on the air bubble surface and then get moved to the top, concentrating the PFAS in the foam and leaving effluent with less PFAS. Then we can have a look at the degradation technologies. So there we really focus on breaking down the actual molecule. And I'll go over a few of the most prominent ones, or the ones that we are looking at now as a solution. The problem is most of these use a lot of energy. So they're very energy, use a lot of energy. So the first one, basically supercritical water oxidation. You can kind of just look at this as a high pressure cooker. The idea is that you take a batch of PFAS contaminated water, you put it in a vessel where you increase the temperature and pressure, basically going through all the states of water. Liquid water will turn into vapor, vapor will turn into supercritical water, and this has the potential to break down PFAS. One of the negative aspects of this treatment, although it's very efficient, let's say it can remove a lot of PFAS and completely mineralize them. Well, what you're doing is also acidifying the solution a lot. So basically, this is not something we can use for example, drinking water. You will still have to treat the water after the treatment of the one other treatment which is investigated is a plasma treatment. What you do with plasma treatment is basically you take an ionized gas and you direct it to the PFAS solution, which will basically create also radicals that can degrade PFAS. But as I said, these and the rest that I will name now were like thermal treatment, incineration, sonic chemical degradation, and photochemical degradation use a lot of, they're very energy intensive. So not an ideal solution. Another one which has shown a lot of promise is electrochemical oxidation. And that's also a little bit what we are looking into in our group. So electrochemical oxidation has, as being one of a heterogeneous treatment, has one advantage, that it works through direct electron transfer. As I said, these molecules are very resistant. So what you have to do before these substances can be attacked by radical species like basically make them unstable. So this is what happens with electrochemical degradation. Once these PFAS touch the anode, there will be an electron that is extracted from the PFAS, rendering them a little more vulnerable to attacks from hydroxyl radicals, also produced within the same technology or the same treatment. So ideally, what you would have is that it mineralizes completely at the anode, forming hydrogen, fluoride, and CO2. And on the cathode side, you would have always formation of H2 and hydroxide. There are some commercial anodes like BDD, which is boron doped diamond, mixed metal oxide, and titanium suboxide that have shown promise to degrade PFAS. The problem here is that these commercial anodes, they also form toxic byproducts. They will also oxidize chloride, which is naturally present in many different types of water, and produce toxic byproducts. So basically rendering the stream, let's say, as toxic as with the PFAS in them. So that is an issue that needs to be treated or needs to be focused on. And what we are doing in our group, in our research group, is we invented a material, an anode material that is based on reduced graphene oxide. There's a SEM image on the right, and you can see it's basically a fibrous material which is coated with reduced graphene oxide, which gives it a high surface area, which is obviously good for this direct electron transfer since it's a surface reaction. So we have a lot of surface that can basically interact with the PFAS. And moreover, the most special thing about it is that it has a low current efficiency for chloride oxidation, or so it doesn't form these toxic byproducts. We saw that this technology got a lot of attention since it's a very promising step towards the, I would say, ideal solution for PFAS treatment. And that is why we started looking into scaling up our technology and bringing our technology to the market. So initially, we started with very small lab reactors, as you can see on the left. And what we are doing now is we're in the process of scaling up this technology to be able to have a sort of a prototype that we can actually use and in the end offer the industry as a PFAS removal technology or destruction technology. So what were kind of like the steps we went into? Where we looked up at the scale up of our technology, but also once you want to bring a technology to the market, you also have to think about basically creation of a company around it that can bring it to the market, that can sell it, and people and a team that can actually do all of this. And so maybe also the message I wanted to bring with this presentation is there's a lot of persistent contaminants. We have a lot of issues with environmental technologies. So there's a lot of opportunities also. So if you have a technology that you see is quite promising, don't leave it into the lab to die at the end of your PhD or the end of your research. But there's a lot of capacity building programs out there that can help you maybe bring this technology and offer it to society, because there's a lot of technologies that kind of like stay in the lab and we have a solution for society, but there's nobody who brings it out and yeah, what offers the solution we actually need, basically. So with this, I'd like to thank you.
Does anyone have questions? Okay.
Mm-hmm. Well, we're definitely going to have to start including these technologies in well, the full treatment train. I would say Yeah, one of the issues is that we have to find opportunities where to apply them, because these PFAS, we can, for example, start phasing them out of the industry. Although there's a lot of industries which have already openly said, well, look, we cannot take this out. It's a molecule, it's a substance that is very particular. If we ban it now, well, the whole production stops. So they're unable to phase it out. So we'll have to really find a solution to treat them. There's no other way. So that kind of like opens up a door and opportunities for these technologies to be further developed and brought to the market also. The thing is that what we see going through this whole process of bringing it to or out of the lab is that there's still not really a faith in all of these technologies. So we would need for I don't know, maybe industry or municipalities to kind of offer the opportunity to try to test, to do some feasibility studies, etc., so that we can learn a lot and further develop and maybe offer them the right solution. So it's kind of like yeah, offering us or opening the door and having a little faith in what we're doing. Mm. Yeah. Yeah, actually, somebody explained it to me like this. I thought it was a very interesting way to look at it. And I think more and more people will have to start looking at it because, well, these companies are making a lot of profit, but they're not seeing what kind of negative effects they're having. Yeah, definitely. I think, yeah, exactly. I think this is, I made the example for PFAS, but I think you can draw the line for all contaminants and yeah. Thank you.